Hi, everybody. This is a presentation about some of the properties of liquids and how they relate to intermolecular attractions. I will refer to a couple things in your textbook, so if you have that handy, that might help you out with this particular presentation. By the end of this lesson, you're going to be able to understand these things, and you're welcome to pause this and read through that. But the first thing is volatility. Now, volatility is the tendency of a liquid to vaporize. And if you have a liquid that has weak attractions between neighboring molecules, then they escape from one another more easily, and the liquid is said to have like a higher volatility or be more volatile. Maybe where you'd see that word is, I've seen it posted before at gas stations, where it'll say like no smoking volatile liquids. And that's because gas is a liquid that vaporizes very easily and then also, of course, happens to be flammable. But, you can think about other liquids that vaporize pretty easily. One of them that everybody's using, on their hands would be hand sanitizer. Okay. And it's the alcohol in hand sanitizer that vaporizes pretty easily because the intermolecular attractions are a little bit weaker than the intermolecular attractions in water. So how this plays in then to something we call vapor pressure of liquid, okay, is that liquids, if they have volatility, which many of them do to a certain degree. Some of them are highly volatile. Sometimes they're just slightly volatile. But they'll build up a pressure that will exist in equilibrium. The vapor will exist in equilibrium with the liquid that's in the container. And this is where, if you look on page 426 in your textbook, they show like some sort of flask that has a liquid in, and a vacuum is drawn in that area above, the liquid. And so if we would use this water bottle and think like, okay, if there's only water, down here in the bottom, and we were able to, create a vacuum up here in this top area and seal it off, water could still evaporate and fill that top space. Now, you look at the other picture then, it says over time, it has a little arrow pointing to the right. When you build up vapor in that space above, the vapor could also recondense back into the liquid form. And you can see a graph there of the plot of pressure versus time if you're looking on page 426. And you can see that eventually, like at the beginning, hold on. At the beginning, this process is happening faster. As vapor builds up, this one starts to happen faster, and this one slows down, and they hit a point where they're happening at the same rate, and that's said to be equilibrium. Okay. Now, equilibrium would change if the temperature changes. Like if we would heat this liquid up, then that would make maybe this, water evaporate faster and slow this process down. And then we would get a higher vapor pressure at a higher temperature. You can look on page 200 of your textbook, and you can see how at different temperatures, the vapor pressure that would build up in this space right here changes. At higher temperature, you can get higher vapor pressures building up. So why is that important? Well, like think about, for example, humidity. In the summer when the air temperature is hotter, it's able to hold more water. You can develop a higher vapor pressure of water. And so we get a higher humidity in the summer. In the winter, when the air temperature is colder, the air can't hold as much water and the air becomes much drier. And we notice that, with how our skin, nose, eyes, lips, etc. feel. So vapor pressure that builds up depends on the temperature. Now, one of the things I wanted you to just look at, okay, very quickly, what's the boiling point of water? Okay, you guys know that's 100 degrees Celsius. Refer to the chart on page 200. What's the vapor pressure of water at its boiling point? Do you notice that it's 760 millimeters of mercury? That ought to look a little familiar because we learned about that at the beginning of the unit, that is normal atmospheric pressure, okay? The normal boiling point of water is 100 degrees Celsius when air pressure is 760. Why does water boil at that temperature? Well, if you've got a beaker full of water, and you know it's boiling when you get a bubble under here. The vapor pressure in the bubble, because it's just full, it's not air, that's water vapor in that bubble that forms under the surface of the water. The vapor pressure that's in there has to at least equal the air pressure that's pushing down on the surface of the water. If they're not equal, the water won't boil. So the temperature at which water boils depends on the air pressure, because you need a vapor pressure that's equal to air pressure for the liquid to boil. So when we're at normal atmospheric pressure, which is 760 millimeters of mercury, the water has to be 100 degrees Celsius to get 760 millimeters of mercury inside of that bubble. Now, if air pressure changes, temperature changes, that is required to get a vapor pressure in the bubble to match the air pressure. Okay, so get rid of all this a second. Go back to having a writing utensil. So when air pressure changes, you get a different boiling point. So think about it. What are some of the situations where air pressure is different than 760 millimeters mercury? So as you were thinking, if you were thinking about weather, like, changes in pressure, was the weatherman talks about high and low pressure, or elevation, which is a big one. That affects air pressure a lot, okay? These types of changes, weather changes and elevation changes, do have an effect on the boiling point of water. And so water only boils at 100 degrees Celsius at normal atmospheric pressure. If you go to a higher elevation, then the air pressure is going to be less and the boiling point of water is going to be less. So, you could look up the elevation of, of Dallastown, okay? And the elevation for Dallastown is oh my, I thought that would be a little bit, let's go with, hold on, is 876 feet, okay? Which might seem like a lot, but if you look up the highest elevation in York County, it's up at Ski Round Top, okay? And at Ski Round Top, it's 1,345 feet. So, that's significantly higher. But even that isn't really that high. If you look up the elevation in Denver, Colorado, that is 5,280 feet, which maybe you recognize that as the conversion from miles to feet. I'm not sure if you recognize that, but that's why they call Denver the Mile High City, because it is 1 mile above, sea level. And so when you're at this high elevation, air pressure is less, which causes the boiling point of water to be less. How much less? In Denver, Colorado, water boils in Denver at 95 degrees Celsius instead of 100 degrees Celsius, which means the water isn't as hot, and that changes like how food will cook in boiling water. One of the things you could do, if you want to do a little activity, I know we can't do labs, but you could look at the cooking directions on a boxed food item. And most boxed food items have high altitude cooking directions. And that's because at high altitudes, water boils at a lower temperature. You might think Denver is the highest, but if you go into the mountainous areas of the Rocky Mountains, you get into anywhere from 10,000 to 14,000 feet plus. So 2.5 miles above sea level. You go to like Mount Everest and you're 20 some thousand. So the boiling point of water decreases drastically at the higher altitudes. Some other properties of liquids: all liquids possess what's called a viscosity. It's a measure of its resistance to flow. Things that have a pretty high viscosity, think about like syrup, shampoo, They resist flow. Okay. Substances that have a really strong intermolecular forces of attraction, they have really high viscosities because the molecules are sticking together and they don't flow or run very easily. Now, if you give them a little bit more kinetic energy by heating them, then they flow a lot easier, and we say that the viscosity decreases. Like, I don't know if you ever tried heating up syrup in the microwave, but if you do, it gets really thin and runny because what you've done is given the particles more kinetic energy. They can overcome their intermolecular attractions and they flow much better, and that decreases the viscosity. These are some articles, and you can check this out if you want. You can go to my Moodle, which if anybody wants to enroll in my Moodle, if you're not enrolled already, the enrollment key is Matter. But you can, click on these links within the PowerPoint that I have posted and definitely check them out. It's about viscosity and how it affects things like in motor oil and engines, etc. Another property, surface tension, energy required to break through the surface of a liquid. This is why, for example, like water forms a drop. We know water is polar. That makes the molecule act like a little magnet, and the particles stick together and form a drop. Okay. So the better molecules attract to each other, the more they have surface tension. And that's a good thing. Water has some surface tension. Think about like, little bugs on a lake. They're part of the food chain. They can sit on the surface because the water molecules are attracted to each other. It almost forms like a net supporting, very light things like a lily pad or leaves or little bugs that might float on the surface of the lake. Maybe an activity you can do if you want to take a little water spread, if you have like breadcrumbs or maybe a little pepper or something, it'll float on the surface of the water. But if you add a drop of detergent to that water and, so then get a different cup, put a little detergent in the water, stir it up. Doesn't take much, just a drop or two. And, sprinkle breadcrumbs or pepper, whatever you're using on there. A lot of times they sink right through to the bottom. And that's because the detergent breaks up the surface tension of the water. And that's a good thing. That's detergents break up the surface tension of the water so that when you're washing something, all the dirt goes to the bottom and it's not at the surface where you try to pull your dishes or your clothing or your mop out of the bucket of water. It's not getting covered with all the dirt. It's, floating on the surface. All the dirt goes to the bottom, which is a darn good thing. And so moving on, the last property that you need to be a little bit familiar with is capillary action. The ability of a liquid to move along narrow spaces or cylinders due to adhesive forces. Just two vocab words you need to know. Cohesive is when molecules stick to themselves, like, for example, water sticking to water. That's cohesion. Adhesive forces, think adhesive tape, like the tape sticks to something else. That would be the force of attraction between different molecules. So like water, which is like a little magnet, it's attracted, for example, to a paper towel. And that's why a paper towel, except for the ones at school, will pick up water and dry your hands off or dry the counter off because the water molecules are attracted to the cellulose that's polar, and cellulose is in trees, and then we make paper products and paper towels out of trees, and then the water is attracted to that molecule and sticks to it, and the paper towel can pick it up. So then this is why, for example, why does water form a meniscus in a graduated cylinder? You guys, and I'm a terrible drawer, you all know that, but water, remember, forms this little meniscus in the graduated cylinder. And while the water sticks to itself and that keeps it from vaporizing too much and floating away, the water is also attracted to the glass and tries to climb the sides. It can only climb so far, though, because the weight of the water does tend to, pull it back down. And as a result, that weight prevents the water from climbing too far. However, if you have a really super narrow cylinder and the water is attracted to the glass or whatever else makes that, tube or cylinder, the water will just be attracted to it and keep climbing because you don't have the weight build up, to draw it back down. So, if you check out these websites, also like trees and capillary action, that's how the water gets from the roots up to the leaves. I read somewhere that like a big tree, like a huge one, can move thousands of pounds of water a day from the roots to the leaves by capillary action. They give you all the vocabulary in there, like um, trees have long tubes. They're called, I think it's pronounced xylem, and they're made of cellulose, and the water is attracted, so it just keeps moving up. And then capillary action helps your heart. The blood in your body is attracted to the materials that make up the walls of your capillary. And that helps, you've got little capillaries and your blood is coming in and traveling through. Your blood is attracted and it keeps moving through, and then your heart doesn't have to work quite as hard. All of that is explained in more detail in these. So if you're interested in them, again, you can, look on the Moodle, find the PowerPoint, and click on these links and check it out. Or you can just Google these things yourself and probably find articles about how capillary action helps trees and, helps your heart. So hopefully this presentation, oh, I forgot about that one. Here, the adhesive forces in the graduated cylinder, the adhesive forces are greater than the cohesive forces. So the water climbs the sides. Sorry. So hopefully you learned a little bit about each one of these. And you're welcome to refer back to this when you're answering questions later. So take care.